Welcome back, friend. I'm so happy you've decided to join me on another journey. Thank you for carving out this moment just for you, a time to get comfortable and allow the static of your day to finally go quiet. Tonight, we're going somewhere rather extraordinary. We're going to explore the vast archipelago of star cities scattered across the cosmos. Billions upon billions of them, each one a massive congregation of stars, dust and dark matter spinning in the darkness. We're talking about galaxies. It's quite the story, actually. From the moment humans first realized our Milky Way wasn't alone in the universe, through the discovery of trillions of these cosmic islands, right up to the present day where we're peering at galaxies so distant, their light has been travelling toward us for over 13 billion years. And then we'll look forward into an almost incomprehensibly distant future, where galaxies will drift so far apart that future civilizations might think they're alone in the universe. It's a journey that spans from the first few 100 million years after the Big Bang to trillions of years in the future, and somehow the whole grand story lands right here with you. In fact, if you need a moment to go get comfy, put on your pajamas, make one last cup of tea, feel free to press pause. It's all right. I'll wait. That's the nice thing about being a recording. I've got all the time in the world. Before we begin, I'm curious. Where are you listening from tonight? Which part of the world are you from? It always intrigues me. Leave a comment and let me know. I'd love to get to know you all more, and I appreciate you being here. There's something rather marvellous about thinking of all of you scattered across this one galaxy, about to learn about trillions of others. And if you enjoy these gentle wanderings through the cosmos, a like and a subscription would be enormously appreciated. It truly helps this little channel find more people who enjoy drifting off to someone rambling about cosmic structures and the ultimate fate of the universe. For those of you who've been here before, thank you. Your continued presence in this small community of curious, drowsy minds means the world to me. Now, I'm not going to attempt to keep you up until sunrise. Sleep is absolutely the objective here. Well, hopefully. But if you do find yourself still awake by the end, I hope you'll drift off with your mind gently full of spiral arms, galactic collisions, and the rather humbling fact that everything you can see in the night sky is just one galaxy among trillions. Rather puts things in perspective when you think about it. Right then, shall we begin our journey through the universe's greatest archipelago? Right, let's start with a rather spectacular disagreement. Picture this. April 26th, 1920, Washington, D.C., the Smithsonian Museum of Natural History. Two astronomers are about to have what would become known as the Great Debate, and the subject of their argument was essentially, how big is the universe? On one side, Harlow Shapley, who believed the Milky Way was absolutely massive and that everything we could see belonged to it. Those fuzzy spiral nebulae people kept spotting through telescopes. Just gas clouds within our own galaxy. The universe was one enormous galaxy, and we were in it. On the other side, Heber Curtis, who thought those spiral nebulae were actually separate galaxies entirely. Island universes, he called them. The Milky Way was just one galaxy among many, possibly millions. They were both accomplished scientists, they both had evidence, and they both couldn't be right. It's the sort of scientific disagreement that makes you wish they'd settled it with a proper duel rather than lectures and slides, though admittedly that might have been frowned upon. The thing is, this wasn't just academic posturing, this was fundamental. Is the universe one galaxy, with us somewhere in it? Or is it an incomprehensibly vast space filled with countless separate galaxies, each one a colossal city of stars? The answer rather changes everything about our place in the cosmos, doesn't it? For context, humans had only recently figured out what galaxies even were. For most of history, that glowing band across the night sky, the Milky Way, was just a mystery. The ancient Greeks thought it was milk sprayed across the heavens. The Chinese saw it as a celestial river. Shakespeare called it that Milky Way which nightly as a circling zone thou seest. Poetic, but not terribly helpful scientifically. It wasn't until Galileo pointed his telescope at the Milky Way in 1610 that anyone realized it was made of stars. Countless stars packed so densely they blur together to form that luminous stream. But nobody knew how big it was, what shape it had, or whether anything existed beyond it. By the early 1920s, telescopes had improved dramatically. Astronomers were cataloguing fuzzy patches of light scattered across the sky. Most assumed these were nebulae, clouds of gas within our own galaxy, but some of these nebulae looked oddly spiral-shaped. And some astronomers, Curtis among them, suspected they might be far more distant and far larger than anyone imagined. The debate in 1920 ended inconclusively. Both men made compelling points. Both had gaps in their arguments. The audience probably left more confused than enlightened, which is often the case with academic debates, isn't it? But then, just a few years later, everything changed. An astronomer named Edwin Hubble, yes, the telescope is named after him, was working at the Mount Wilson Observatory in California, using what was then the world's largest telescope, and he was looking at one particular fuzzy spiral, the Andromeda Nebula. Hubble managed to identify individual stars within Andromeda. More importantly, he identified a specific type of star called a Cepheid variable, which brightens and dims in a predictable pattern. And here's the clever bit. The period of that pattern tells you how bright the star actually is. Compare that to how bright it appears from Earth, and you can calculate its distance. When Hubble did the calculations for these Cepheid variables in Andromeda, the result was staggering. Andromeda wasn't inside the Milky Way. It was nearly 1 million light-years away, far beyond our galaxy's edge. It was, indisputably, a separate galaxy. Curtis was right. The Milky Way wasn't the universe. It was one galaxy among many. And if Andromeda was a separate galaxy, then presumably all those other spiral nebulae were too. The universe has just become exponentially larger. Can you imagine that moment? The sudden realization that everything visible around you is just one island in an ocean of islands. That the universe isn't one thing but countless things, scattered across distances so vast they make interstellar space look cozy. Hubble's discovery in 1924 is one of those pivotal moments in human understanding, right up there with realizing the Earth orbits the Sun, or that we evolved from other species. It fundamentally relocated humanity in the cosmos. We weren't just on a planet orbiting a star. We were on a planet orbiting a star in a galaxy that was one of many galaxies. And as telescopes improved, many became an understatement of cosmic proportions. Hubble, the man, not the telescope, kept looking. He found more galaxies, and more, different shapes, different sizes, scattered in every direction. The universe wasn't just bigger than we thought, it was unimaginably bigger. Today, our best estimates suggest there are around 2 trillion galaxies in the observable universe. 2 trillion! That's 2 trillion separate galaxies, each containing millions or billions or even trillions of stars. The Milky Way, our home, contains somewhere between 100 to 400 billion stars, and it's just one of 2 trillion galaxies. Let that settle in your mind for a moment. Every point of light you see in the night sky is a star in our galaxy. But between those stars in the dark spaces there are trillions of other galaxies too far away to see without a telescope. Each one a massive congregation of stars, most with their own planets, their own stories. Rather humbling, isn't it? Every human drama, every war, every love story, every triumph and tragedy in recorded history happened on one planet, orbiting one star, in one galaxy among 2 trillion. Puts that argument you had with someone about where to go for dinner in a certain perspective. But here's what I find even more remarkable. We figured this out. Humans, with our brief lifespans and limited senses, managed to look at fuzzy patches of light and deduce not just that they were distant galaxies, but how distant they were and how many existed. We went from thinking the Milky Way was everything to knowing it's one grain of sand on an infinite beach, all in less than a century. So when Shapley and Curtis had their debate in 1920, they were arguing about the size of everything. 4 years later, Hubble settled it. The universe was bigger than Shapley thought, much bigger, and it was about to get even bigger because Hubble's next discovery would reveal something nobody expected. The universe itself was expanding, carrying galaxies away from each other at incredible speeds. But we're getting ahead of ourselves. Before we talk about where galaxies are going, let's talk about what they actually are, shall we? So what exactly is a galaxy? At its simplest, it's a massive collection of stars, dust, gas, and dark matter, all held together by gravity. But that's rather like describing a symphony as a collection of sounds. Technically accurate, but missing the grandeur entirely. Galaxies are among the largest gravitationally bound structures in the universe. They range from dwarf galaxies with a few billion stars to giants with trillions. They spin, they collide, they merge, they birth new stars and watch old ones die. They're dynamic, evolving systems that change over billions of years, and they come in different varieties classified by their shapes. Astronomers, with their characteristic flair for the obvious, named them based on what they look like. First, you have spiral galaxies. These are the show-offs of the galaxy world. They have a central bulge of older stars surrounded by a flat disk with beautiful spiral arms. The arms aren't solid structures but density waves where stars, gas and dust pile up, like traffic jams on a cosmic motorway. Star formation happens in these arms, which is why they often glow blue from young hot stars. Our Milky Way is a spiral galaxy, specifically a barred spiral. Barred means it has a straight bar of stars through the centre, with the spiral arms extending from the ends of the bar. About 2/3 of spiral galaxies are barred, which makes us reasonably common, at least in that respect. The Andromeda Galaxy is also a spiral. In fact, it's the nearest large galaxy to us, about 2.5 million light-years away. That's our closest cosmic neighbour, and it's heading toward us at about 110 kilometers per second. Don't worry, we've got about 4 billion years before we collide. Plenty of time to prepare, perhaps put the kettle on. Then you have elliptical galaxies. These are shaped like stretched out spheres or rugby balls, or American footballs if you prefer, though I find it's a poor name for a sport where the ball is barely involved with feet, but I digress. elliptical galaxies contain mostly older red stars and have very little gas and dust left for forming new stars. They're the retirement communities of the galaxy world, full of elderly stars quietly burning out. Elliptical galaxies range from nearly spherical to highly elongated. They're classified E0 to E7, with the number indicating how stretched they are. E0 is almost round. E7 is quite elongated. Astronomers are nothing if not systematic, even if the system is a bit dull. The largest galaxies in the universe are ellipticals. IC1101, for instance, is a supergiant elliptical galaxy, about 1.04 billion light-years away. It contains roughly 100 trillion stars. That's 1,000 times more stars than the Milky Way. Wrap your mind around that for a moment. If each star in the Milky Way represented 1 second, IC1101 would represent over 3 million years. It's preposterously large. Then there are irregular galaxies. These are the galaxies that don't fit neatly into the other categories. They have no particular shape, just messy collections of stars and gas clouds. Often they're small galaxies that have been gravitationally disrupted by larger neighbours, the universe's cosmic ruffians, if you will. The large and small Magellanic Clouds, visible from the southern hemisphere, are irregular galaxies. They're satellite galaxies of the Milky Way, smaller galaxies in orbit around our own. We have several dozen of these satellite galaxies, most too faint to see without a telescope, all gravitationally bound to us. There's also a fourth category, lenticular galaxies. These are intermediate between spirals and ellipticals. They have a central bulge and a disk like spiral galaxies, but no spiral arms. They've used up most of their gas and dust, so they're not forming many new stars. Sort of spiral galaxies that have let themselves go a bit. Now here's something interesting. Galaxy shapes aren't random. They're related to the galaxy's history. Spiral galaxies are relatively young and active, still forming stars. Elliptical galaxies are often older and have usually formed from mergers of smaller galaxies. When two spiral galaxies collide, the result is often an elliptical. All that structure gets scrambled by the collision. Speaking of collisions, galaxies don't exist in isolation. They're part of groups and clusters, gravitationally bound collections of galaxies. The Milky Way is part of the local group, which contains about 80 galaxies. Most are small dwarf galaxies, but there are 3 large spirals: the Milky Way, Andromeda, and Triangulum. Beyond groups are clusters, which can contain hundreds or thousands of galaxies, and beyond clusters are superclusters, structures containing multiple galaxy clusters. The Milky Way is part of the Virgo supercluster, which contains around 47,000 galaxies spread across 110 million light-years. But even superclusters aren't the largest structures. Galaxies are distributed in vast cosmic webs, sheets, and filaments separated by enormous voids. If you could zoom out and see the distribution of galaxies across billions of light-years, it would look like a 3-dimensional spider's web, with galaxies concentrated along the strands and vast empty spaces between. These structures formed from tiny density variations in the very early universe. Regions slightly denser than average attracted more matter gravitationally, becoming denser still, eventually forming galaxies and galaxy clusters. The universe's largest structures are fossils of quantum fluctuations from the first fractions of a second after the Big Bang. Rather extraordinary when you think about it. Now, how do we actually observe all these distant galaxies? After all, light takes time to travel. When we look at Andromeda, we're seeing it as it was 2.5 million years ago. Look at a galaxy a billion light years away, and you're seeing it as it existed a billion years ago, long before complex life existed on Earth. This means telescopes are time machines. The farther away we look, the further back in time we see. The most distant galaxies we've observed are more than 13 billion light-years away. We're seeing them as they were just a few 100 million years after the Big Bang, when the universe was young and galaxies were just beginning to form. These early galaxies look different from modern ones. They're smaller, more irregular, more chaotic. They're galaxies in their infancy, and studying them tells us how galaxies evolve over cosmic time. The James Webb Space Telescope, launched in 2021, is specifically designed to observe these early galaxies in unprecedented detail. It detects infrared light, which can penetrate dust clouds and reveal distant galaxies whose light has been stretched to infrared wavelengths by the expansion of the universe. Early results from Webb have been extraordinary. It's finding galaxies farther and earlier than expected, some appearing surprisingly mature for their age. These observations are forcing astronomers to revise theories about how quickly galaxies formed after the Big Bang. Turns out the universe was busier in its early days than we thought. But here's the thing. Despite having 2 trillion galaxies to observe, we still don't understand everything about them. We don't fully know why some become spirals and others ellipticals. We don't understand all the details of how supermassive black holes form at their centers. We're still figuring out the role of dark matter in galaxy formation. And that's rather exciting, isn't it? Even after a century of studying galaxies, there are still mysteries. The universe keeps surprising us, revealing complexity we didn't expect, forcing us to refine our understanding. So there you have it. 2 trillion galaxies, each one a vast collection of stars and worlds, scattered across an expanding universe, organized into groups and clusters and superclusters, forming a cosmic web of unimaginable scale. And somewhere in one spiral arm of one galaxy, on one planet orbiting one star, you're lying there listening to someone explain all this while trying to fall asleep. Rather remarkable, really. Sleep well knowing you're part of one island in an ocean of 2 trillion islands. Right, let's wind the clock back, way back, to the beginning of everything. Roughly 13.8 billion years ago, the universe began in what we rather dramatically call the Big Bang. In the first fractions of a second, everything that would ever exist appeared in an incredibly hot, dense state and began expanding, and it's been expanding ever since. But here's the thing. The very early universe didn't have galaxies. It didn't even have stars. For the first 380,000 years, it was too hot for atoms to form. It was just a plasma of particles and radiation, completely opaque. Light couldn't travel far before being absorbed and re-emitted. The universe was essentially a hot fog. Then, as it expanded and cooled, something crucial happened. The temperature dropped enough for electrons and protons to combine into hydrogen atoms. This moment is called recombination, and it made the universe transparent. Light could suddenly travel freely. This first light, released about 380,000 years after the Big Bang, is what we now detect as the cosmic microwave background radiation. If you've seen those maps of the CMB with slightly different colours representing tiny temperature variations, you're looking at the universe as it was 380,000 years old. It's literally the oldest light in the universe, a baby photo of everything. stretched to microwave wavelengths by expansion. After recombination, the universe entered what astronomers poetically call the Dark Ages. No stars had formed yet. The universe was transparent but dark, filled with neutral hydrogen gas with tiny density variations inherited from quantum fluctuations in the early universe. Those density variations were crucial. Regions slightly denser than average had slightly more gravitational pull. They attracted more hydrogen, which made them denser still, which increased their gravity further. This positive feedback loop caused matter to clump together, forming denser and denser regions. But it took time. Gravity works slowly on cosmic scales. For about 100 million years, the universe remained dark, with hydrogen slowly collecting into denser pockets, while the universe continued expanding. Then, somewhere between 100 and 250 million years after the Big Bang, the first stars formed. These weren't like modern stars. They formed from pure hydrogen and helium, the only elements that existed. No carbon, no oxygen, no iron, just the two lightest elements. These first stars, called population 3 stars, were likely enormous, perhaps 100 to 1,000 times the Sun's mass. At those sizes, they would burn incredibly hot and bright but die young, possibly surviving only a few million years before exploding as supernovae. When these massive stars exploded, they created something new. Heavier elements, carbon, oxygen, nitrogen, silicon, iron, all forged in the cores of stars and scattered into space by supernova explosions. The universe was gradually being enriched with elements beyond hydrogen and helium. We've never actually observed a population 3 star directly. They all died billions of years ago. But we've seen their chemical signatures in very old stars that formed from gas clouds enriched by population 3 supernovae. We're reasonably confident they existed, even if we haven't caught one in the act. Now, these early stars didn't form randomly scattered across space. They formed in the densest regions, where the most gas had collected. And as more stars formed in these regions, something remarkable happened. They became gravitationally bound together. The first galaxies were being born. The earliest galaxies were small, perhaps containing only a few million stars, tiny compared to modern galaxies. But they were the seeds from which everything else grew. This period, when the first stars and galaxies formed and began lighting up the universe, is called the Cosmic Dawn, or the Epoch of Reionization. Reionization because the ultraviolet light from these early stars was energetic enough to strip electrons from hydrogen atoms, ionizing the gas that filled space between galaxies. Gradually, over hundreds of millions of years, nearly all the hydrogen in the universe became ionized again. The Dark Ages ended. The universe was full of light from billions of young galaxies, each one a collection of hot, bright stars illuminating the primordial gas around them. The James Webb Space Telescope has given us glimpses of these early galaxies. They're small, irregular, often actively forming stars at prodigious rates. They don't look like the grand spirals we see today. They're scrappier, more chaotic, the building blocks from which larger galaxies would eventually form. Because here's what happened next. These early small galaxies didn't stay small. Gravity kept working. Galaxies attracted each other. They merged, combining their stars into larger galaxies. Some grew by accreting gas and forming new stars. Over hundreds of millions of years, small galaxies became large galaxies. By about 1 billion years after the Big Bang, recognizable structures were emerging. Galaxies were organizing into groups. The cosmic web was taking shape, and at the centers of many galaxies something strange and powerful was forming: supermassive black holes. We're still not entirely sure how supermassive black holes formed so early. These aren't stellar mass black holes formed from collapsed stars. These are monsters, millions or billions of times the Sun's mass, somehow appearing within the first billion years of the universe. They might have formed from the collapse of massive gas clouds, or from chains of stellar mergers, or from the direct collapse of very massive population 3 stars. Frankly, we're still figuring it out. What we do know is that these black holes became central to galaxy evolution. They don't just sit there passively. As matter falls toward them, it forms an accretion disk, heating to millions of degrees and emitting enormous amounts of energy. These active galactic nuclei can outshine their entire host galaxy, pumping energy and radiation into the surrounding space. This energy affects star formation in the galaxy. It can heat gas, preventing it from collapsing to form new stars. It can drive powerful winds that push gas out of the galaxy entirely. The growth of the central black hole and the growth of the galaxy are intimately connected, each influencing the other. By a few billion years after the Big Bang, galaxies were looking more like modern galaxies. Spirals were developing their characteristic arms. Ellipticals were forming from mergers. Galaxy clusters were assembling. The universe was taking on the structure we recognize today. But it wasn't static. It never has been. Galaxies continued evolving, merging, changing. Star formation rates rose and fell. The universe went through phases where stars formed rapidly, and phases where formation slowed. We're currently in a relatively slow period. Peak star formation happened about 10 billion years ago. Since then, it's been gradually declining. Think about that for a moment. The universe is 13.8 billion years old. It took several 100 million years for the first stars and galaxies to form. The universe has spent most of its existence filled with galaxies, slowly evolving, gradually using up the gas available for forming new stars. We're living in what might be called the universe's middle age. Not young and chaotic like the cosmic dawn, but not yet old and dark like the far future. We're in a relatively gentle era, where stars still form, galaxies still evolve, and the universe is still, in its way, alive with activity. And here's the poignant bit. Every atom in your body heavier than hydrogen was forged in a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all created in stellar cores billions of years ago, dispersed by supernova explosions, eventually incorporated into the gas cloud that formed our solar system 4.6 billion years ago. You're not just in the universe, you're made of it. You're stardust, quite literally, assembled into a configuration capable of contemplating its own cosmic origins while lying in bed trying to fall asleep. Rather beautiful when you put it that way, right? Sleep well knowing you carry the cosmic dawn within you. So we've established that galaxies form, they grow, they change. But what actually happens in a galaxy's life? Do they just sit there spinning peacefully for billions of years? Well, no. Galaxies have rather dramatic lives, full of violence, mergers, and occasional bouts of frantic activity. They're quite exciting once you get to know them. Let's start with something deceptively simple. How galaxies rotate. Spiral galaxies spin, which is why they have that distinctive shape. But here's the odd thing. They don't rotate like solid objects. Different parts rotate at different speeds. Stars near the centre orbit faster than you'd expect, and stars far from the centre orbit faster than they should based on visible matter alone. This observation led to the discovery, or rather the acceptance, of dark matter. There's far more mass in galaxies than we can see. This invisible mass, called dark matter, makes up about 85% of the matter in the universe. We can't see it directly, but we can detect its gravitational effects. It's what holds galaxies together and explains their rotation patterns. Dark matter forms halos around galaxies, extending far beyond the visible edges. These halos are what really define a galaxy's gravitational reach. The visible galaxy, all those lovely stars we can see, is just the tip of the iceberg. Most of the galaxy's mass is invisible, spread throughout a much larger halo. Right, moving on to more dramatic events. Galaxy mergers. Remember how I mentioned galaxies exist in groups? Well, gravity keeps them interacting. Over billions of years, galaxies orbit each other, sometimes passing by, sometimes colliding. When two galaxies collide, it's not like two objects smashing together. Stars are spread so far apart that actual stellar collisions are incredibly rare. Instead, the two galaxies pass through each other, their gravitational fields interacting, pulling on each other's stars and gas. The result is spectacular. Stars get flung into new orbits. Gas clouds collide, triggering massive bursts of star formation. The galaxy's shapes distort, creating tidal tails and bridges of stars stretching between them. Over hundreds of millions of years, the two galaxies merge into one, their stars mixing, their supermassive black holes eventually coalescing at the center. The Andromeda Galaxy is heading toward us, remember? In about 4 billion years we'll collide, or rather, our descendants will witness it, assuming there are any. The collision will take about 1 billion years to complete, during which the night sky will be truly spectacular, full of tidal streams and newly forming stars. The solar system will likely survive intact. Individual stars almost never collide, but we might get flung into a different part of the merged galaxy, possibly even ejected into intergalactic space. The sun will continue shining regardless, at least until it becomes a red giant and consumes the Earth. But that's a different cosmic catastrophe altogether. When the Milky Way and Andromeda finish merging, the result will be a giant elliptical galaxy. Astronomers have already named it Milkomeda, or sometimes Milkdromeda. We're nothing if not creative with portmanteaus. Galaxy mergers aren't rare. They're a fundamental part of galaxy evolution. Most large galaxies, including the Milky Way, have grown partly by cannibalizing smaller galaxies. We're currently in the process of absorbing several dwarf galaxies. Their stars are gradually being pulled into our galaxy, their original structures torn apart by tidal forces. It's galactic cannibalism, and it's perfectly normal. In fact, if you look at the Milky Way's stellar halo, the sparse region of stars surrounding the main disk, you'll find streams and clusters of stars that once belonged to other galaxies. They're the remnants of past mergers, fossil evidence of our galaxy's violent past. Then there are starbursts. Sometimes, when gas clouds collide during a merger, or when a galaxy encounters a dense region of intergalactic gas, something remarkable happens. A massive burst of star formation. Hundreds or thousands of stars form in a relatively short period, perhaps just a few million years. These starburst galaxies are spectacular. They're forming stars at rates hundreds of times faster than the Milky Way. They burn through their gas quickly, creating brilliant, short-lived spectacles of stellar birth. Eventually, they exhaust their gas supply, and the starburst ends, leaving behind a population of young stars. Galaxy evolution is also influenced by environment. Galaxies in dense clusters experience different conditions than isolated galaxies. In clusters, galaxies move through hot, diffuse gas that can strip away their own gas reservoirs, a process called ram pressure stripping. This shuts down star formation, gradually transforming spiral galaxies into gas-poor lenticulars or ellipticals. Clusters also have higher rates of galaxy interactions. More neighbours means more opportunities for close encounters, harassment and mergers. Cluster galaxies tend to be older and redder than field galaxies, having used up or lost their gas long ago. There's also something called galactic feedback. Remember those supermassive black holes at galaxy centres? When they're actively accreting matter, they don't just sit there quietly. They generate powerful winds and jets that can blow gas out of the galaxy entirely. This regulates star formation, preventing galaxies from converting all their gas into stars too quickly. Without feedback, galaxies would form stars far more efficiently than observed. They'd be more massive with different properties. Feedback from supernovae and active galactic nuclei is crucial for producing galaxies that match what we actually see. All of this means galaxies aren't static. They're dynamic, evolving systems shaped by internal processes and external interactions. They grow through mergers and accretion. They form stars in bursts and lulls. They interact with neighbours and with the intergalactic medium. They change over billions of years, and no two have identical histories. The Milky Way itself has had quite a life. It formed over 13 billion years ago from the merger of smaller protogalaxies. It's absorbed dozens of smaller galaxies over its lifetime. About 10 billion years ago, it merged with a dwarf galaxy called Gaia Enceladus, an event that significantly influenced our galaxy's structure. And it's still evolving, still accreting satellite galaxies, still forming new stars in its spiral arms. Where are we in the Milky Way, by the way? We're in the Orion Arm, a minor spiral arm about 26,000 light-years from the galactic centre. We orbit the centre once every 225 to 250 million years. The last time we were in this position, dinosaurs were just beginning to dominate the Earth. The next time we complete an orbit, who knows what will exist on Earth, if anything. It's worth pondering, isn't it? Our entire recorded history, every civilization, every empire, every human who's ever lived, all of it has occurred in less than 1,000th of a galactic year. We're a brief flicker in the Milky Way's long story. And the Milky Way itself is just one chapter in the universe's story, one galaxy among trillions, each with its own history of formation, evolution, mergers, and transformations. Each one a complex, dynamic system, changing over timescales so vast they make human history look like a brief moment. Right, let's talk about the future. Not the cheerful, optimistic humanity spreads across the stars future. The real future. The long, slow, increasingly lonely future of the universe itself. Because here's the thing, the universe is expanding. Not just expanding, but accelerating. Galaxies are moving away from each other, and they're moving away faster over time. This was discovered in 1998, rather surprising everyone, and it earned its discoverers a Nobel Prize for basically proving the universe is stranger than we thought. The acceleration is driven by something called dark energy, which is honestly a placeholder name for we have absolutely no idea what this is. It makes up about 68% of the universe's energy content, and its effect is to push space itself apart, accelerating the expansion. What does this mean for galaxies? Well, in the near term, not much. Galaxies that are gravitationally bound, like our local group, will stay together. Gravity is strong enough on these scales to resist expansion. The Milky Way and Andromeda will still collide as planned. Galaxy clusters will remain intact. But beyond our local neighborhood, galaxies are moving away. And as the universe expands, they're moving away faster. Eventually, distant galaxies will be receding from us faster than light can travel. Not because they're moving through space faster than light, that's impossible, but because space itself is expanding between us. This creates what's called the cosmic event horizon. Beyond a certain distance, galaxies are receding so fast that light leaving them now will never reach us, no matter how long we wait. Those galaxies have effectively left our observable universe. We can still see them as they were in the past, but their present and future are forever beyond our reach. Over the next few trillion years, more and more galaxies will cross this horizon. The observable universe will gradually empty. First, distant galaxies will fade from view, then nearby clusters. Eventually, only our local group will remain visible. The rest of the universe will have expanded away beyond any possibility of contact or observation. Imagine that. A future civilization, trillions of years from now, looking up at the night sky and seeing only their local cluster of galaxies. Everything else gone, receded beyond the horizon. They might conclude, quite reasonably, that their cluster is the entire universe. They'd have no way of knowing that trillions of other galaxies exist forever beyond their view. When you really think about it, the universe is giving them the ultimate form of social distancing. It's creating these vast, isolated cosmic bubbles, and once a galaxy leaves our bubble, it's gone for good. No visiting, no messaging, not even a wave goodbye. But let's continue forward. What happens within these isolated clusters? Star formation will gradually decline. Galaxies form new stars from gas and dust, but over time that gas is either converted into stars, blown away by stellar winds, or falls into the central black hole. Eventually, each galaxy exhausts its gas supply. Star formation ceases entirely. This process takes a long time. Small red dwarf stars can burn for trillions of years, but eventually even they exhaust their hydrogen and fade away. One by one, stars die and are not replaced. Galaxies gradually darken. By about 100 trillion years from now, maybe a bit longer, star formation in the universe will have essentially stopped. The last stars will be small red dwarfs, slowly consuming their remaining fuel. The universe will be much darker than today, filled with stellar remnants, white dwarfs, neutron stars, black holes. Galaxies will still exist, but they'll be graveyards. Collections of dead stars slowly orbiting their central black holes, illuminated only by the occasional flare when a star gets torn apart by tidal forces. As more time passes, even these structures will decay. Stars occasionally pass close to each other, their gravitational interactions flinging some into different orbits. Over incredibly long timescales, many stars will be ejected from their galaxies entirely, cast into intergalactic space. Others will gradually spiral inward, eventually falling into the central supermassive black hole. This process, called dynamical relaxation, takes an absurdly long time. We're talking 100 billion years. For perspective, the universe is currently only 13.8 billion years old. This future timescale is about 1 billion times longer than the universe has currently existed. But even that's not the end. Eventually, galaxies themselves will evaporate. Most of their stars will either fall into the central black hole or be ejected into intergalactic space. What remains will be isolated stellar remnants drifting through an ever-expanding void and supermassive black holes, the last massive objects in the universe. Now, you might think black holes are eternal. They're not. Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly lose mass and eventually evaporate completely. For stellar mass black holes, this takes an unimaginably long time, a number so vast you'd need to write a 1 followed by 67 zeros. For supermassive black holes like the one at the Milky Way's centre, it takes even longer, a 1 followed by 100 zeros, a timescale called a googol. These timescales are so vast they're almost meaningless. There's no intuitive way to grasp them. The current age of the universe is utterly insignificant compared to these futures. It's like comparing a single second to the age of the universe, except the disparity is far, far greater. But eventually even black holes evaporate. And then what? The universe becomes a cold, dark, diffuse sea of particles, photons, and increasingly sparse matter, all moving away from each other, all cooling toward absolute zero. This is sometimes called the heat death of the universe, where entropy reaches its maximum and nothing interesting can happen anymore. It's rather bleak, to be honest. The universe ends not with a bang, but with an incredibly prolonged, exponentially slow fade to darkness and silence. Now, there are caveats. These predictions assume our current understanding of physics is correct and complete. It probably isn't. We still don't understand dark energy. We don't know if the laws of physics might change over these extreme timescales. There might be processes we haven't discovered that alter this trajectory. Some theories suggest the acceleration might reverse, causing the universe to contract in a big crunch. Others propose a big rip, where acceleration increases until it tears apart galaxies, stars, planets, and eventually atoms themselves. Still others suggest the universe might be cyclical, ending and reborn in endless succession. We don't know. We can't know. Not yet. But based on current observations, the most likely fate is the slow, cold fade-out, the long goodbye. It's humbling, isn't it? All those galaxies, all those stars, all that structure and beauty and complexity, eventually dissipating into darkness. Everything temporary, even on cosmic scales. Nothing lasts forever. But here's another way to look at it. We exist during the universe's brief moment of brilliance. We're here during the era when stars shine, when galaxies swirl in beautiful spirals, when planets orbit those stars and life can emerge on at least some of them. We're living during the universe's golden age, cosmically speaking. In 100 trillion years, the universe will be dark and empty. But right now it's full of light and structure and possibility. And somehow, against all odds, we're here to observe it, to understand it, to marvel at it. That's worth appreciating, don't you think? We're not just in the universe. We're the universe experiencing itself, briefly awake and conscious during its most interesting epoch. Now, one final question before we drift off. Will humans ever reach other galaxies? It's the sort of question that captures imagination. We've already sent probes beyond our solar system. We've walked on the moon. We talk about colonizing Mars, perhaps building habitats throughout the solar system, but other galaxies, that's a different magnitude entirely. The nearest large galaxy is Andromeda, 2.5 million light-years away. With current technology, reaching it is not just difficult, it's impossible. Our fastest spacecraft, Voyager 1, is travelling at about 17 kilometers per second. At that speed, reaching Andromeda would take roughly 44 billion years. That's more than 3 times the current age of the universe. Even if we could travel at a significant fraction of light speed, say 10%, the journey would still take 25 million years. That's longer than humans have existed as a species. It's longer than our entire evolutionary lineage stretching back to early primates. No human could make that journey. Perhaps you could send generation ships, spacecraft where multiple generations live and die during the voyage. But keeping a viable population alive for millions of years, maintaining technology and purpose across thousands of generations, dealing with cosmic radiation and the psychological challenges of isolation, it's almost inconceivable. Or perhaps you could use suspended animation, though we're nowhere near that technology, or upload human consciousness into machines that don't age or die. But at that point, are we still talking about humans travelling to other galaxies, or something else entirely? There's also the small matter of energy. Accelerating even a modest spacecraft to relativistic speeds requires phenomenal amounts of energy. Slowing down at the destination requires just as much. The energy requirements scale such that interstellar travel within our own galaxy is extraordinarily challenging. Intergalactic travel is beyond anything we can currently imagine. Some have proposed exotic solutions, wormholes, hypothetical tunnels through space-time that could connect distant regions. But we don't know if wormholes can exist, much less whether they could be created or stabilized. Warp drives that contract space in front of a ship and expand it behind, allowing faster than light travel without violating relativity. But these require exotic matter with negative energy density, which might not exist. The honest answer is probably not. Barring revolutionary discoveries in physics that give us access to forms of travel we can't currently conceive, humans will likely never reach other galaxies. The distances are simply too vast, the energy requirements too extreme, the timescales too long. And here's the sobering bit: if we can't reach other galaxies, neither can anyone else. If alien civilizations exist in other galaxies, we'll never meet them. We'll never exchange ideas, never compare experiences, never confirm that we're not alone. The universe contains potentially billions of civilizations, all forever isolated in their own galactic islands. As the universe expands and galaxies recede beyond the cosmic horizon, this isolation becomes permanent. Even communication becomes impossible. We're stuck in our local group, and even that will eventually merge into a single elliptical galaxy. That's our cosmic neighborhood, and we can never leave it. It's a lonely thought. The universe is vast beyond comprehension, filled with wonders we'll never see, potentially teeming with life we'll never meet. We're confined to one small corner, unable to bridge the gulfs between galaxies. But perhaps there's comfort in that too. It means whatever we do, whatever we become, happens here, in this galaxy, among these stars. Our story, humanity's story, unfolds in the Milky Way. This is our home, and it's more than enough. Hundreds of billions of stars, countless worlds, millions of years of potential future ahead of us. If we survive, if we spread beyond Earth, our descendants might one day witness the merger with Andromeda. They might live in the resulting Milky Way galaxy, exploring its trillion stars, building civilizations on countless planets. That's a future vast enough to occupy us for millions of years. And if we don't survive, if humanity is just a brief flash in cosmic history, well, we were still here. We still looked up at the stars and wondered. We still figured out what galaxies are, how they formed, where they're going. We still marveled at the vastness and beauty of it all. That counts for something, doesn't it? In a universe that will eventually fade to darkness, we existed during its moment of light. We were conscious, curious, capable of understanding our place in the cosmos. For a brief moment, the universe woke up and looked at itself through human eyes. And right now you're part of that moment. You're lying there, probably quite close to sleep now, contemplating galaxies and cosmic futures and the strange, wonderful fact of your own existence. You're a collection of atoms arranged just right to think about galaxies, which are collections of atoms arranged differently. It's all rather extraordinary when you stop and consider it. The universe made galaxies. Galaxies made stars. Stars made elements. Elements made planets. Planets made life. And life made you. Someone capable of understanding all of it while drifting off to sleep. And that brings us to the end of our journey through the universe's archipelago of galaxies. From that heated debate in 1920 about whether other galaxies even existed, through the discovery of 2 trillion of them scattered across unfathomable distances, from the first light after the Big Bang to the slow fade-out trillions of years. It's been quite the voyage, hasn't it? We've covered rather a lot. The moment Edwin Hubble proved the universe was far larger than anyone imagined, the spectacular variety of galactic shapes and sizes, the chaotic birth of the first galaxies in the cosmic dawn, the dramatic lives they lead full of mergers and starbursts, and finally, the long, lonely future awaiting them as the universe expands into darkness. If my voice hasn't quite done its job and you're still listening, I hope you've at least found a few quiet wonders to carry with you into your dreams. Perhaps it's the sheer scale of it all. 2 trillion galaxies each containing billions of stars. Perhaps it's the realization that we exist during the universe's brightest era, before everything fades away. Or perhaps it's simply the strange comfort of knowing that even in this vast, expanding universe, we're here, briefly conscious, able to understand and appreciate it all. Thank you for spending this time here, for letting me ramble on about cosmic structures and the ultimate fate of everything while you wind down your day. I do hope this helped you relax, that it gave your mind something peaceful to focus on while the day's concerns faded into the background. Before you go completely, I'd genuinely love to know where you're listening from tonight. Leave a comment below and let me know your location and the time. There's something rather wonderful about imagining all of you scattered across this one galaxy, all pondering the existence of 2 trillion others. Also, if you've enjoyed this gentle journey through the universe's greatest archipelago, a like would be enormously appreciated. And if you'd like more of these peaceful explorations through science, do consider subscribing. It truly helps this little channel grow and lets me know there are people out there who enjoy falling asleep to discussions about cosmology and galactic evolution. For those of you who keep returning to these quiet moments, thank you. Your continued presence means more than I can properly express. For anyone still awake, I'll leave you now with some soft ambient sounds to help you drift off properly. If you've already fallen asleep, well, I did something right at least. I hope you have pleasant dreams of spiral galaxies and cosmic webs, of ancient starlight and future darkness, of 2 trillion islands scattered through an expanding universe, each one a world unto itself. Until next time, sleep well and have good dreams. Good night.